Today we're going to talk about CT awareness and safety. And so we're going to look at some safety factors that we need to consider when working on CT circuits and some procedural considerations we also need to pay attention to when we're working on CT circuits. CT circuits are some of the most critical and dangerous circuits that we work with in the substation environment. As I've previously mentioned, there are some serious safety considerations that can present themselves when working on a CT circuit, both in terms of personnel safety and system integrity. So we need to pay attention to all of these factors when working on CT circuits. Only trained personnel should be working on CT circuits in a live substation. And we're going to talk about who that is and what procedures need to be considered and taken into account when working on these CT circuits. The purpose of CTs are to provide some real-time information about the bulk electric system. And it's going to do this in a couple of ways. It's going to do this through system protection so that we're going to be able to see and detect faults on the line, abnormal conditions in the case of we need to remove a line from service or a particular portion of a substation from service. And it's also going to be wrapped up into the financial aspect of the bulk electric system also, and metering CTs, which are going to look at billing and provide the information they need to generate revenue for the utility in the sense of billing and metering that. So we have two main functions from CTs, and that's going to be provide real-time system information for system protection and billing. Why we have them is because frequently the current levels are extremely high and they'd be very unmanageable to work with in their natural state. So what we're going to use the CT for is to make it and transform a high value into an equivalent lower value so that protective relays can then use this information to monitor system conditions. So we're going to take a very large value and make it to a much more manageable value to reduce the size of wires and to make equipment smaller in order to be able to see what's going on without having large wires and large cumbersome pieces of equipment. So the theory behind a CT is no different than any other transformer that we've worked on. We're going to take an induced current and reduce it or raise it to a different value that is equivalent to some conversion of the primary source. So in a normal two-winding transformer, you have your primary side and your secondary side, and there's a number of windings on the primary versus a number of windings on the secondary. And a CT doesn't work really any differently than that. The primary of the CT is the conductor that the CT is around. So if we look at our picture, you can see that the primary current's running through that conductor, and then you have that donut CT around it. The secondary side of that CT is going to be connected to a load of some sort, be it a relay, a fault recorder, or any other piece of equipment that provides some sort of load for that CT to go through. And you can see in our picture there that you have that blue wire wrapped around the core, and it goes to an ammeter, and that's where our secondary current is going. So it doesn't work any differently than a traditional transformer in the sense that it's converting current from one value to another. The secondary current is dependent on the turns ratio, and you can see that to find a turns ratio, we take the rated primary current divided by the rated secondary current, and we can figure out what our turns ratio is. So in the case of, say, a 2000 to 5 CT, you can take 2000 on rated current on the primary divided by 5 rated current on the secondary, and you'll come up with a 400 to 1 ratio. So for every 400 amps that passes through the primary, you will see 1 amp on the secondary. You can look at this, and this is a common schematic you'll see. Here we have a set of CTs right here and another set of CTs here. One says from breaker 1305, another from 1317. You'll see that they join together and that they go, and here this GE D60 is our load. Something to pay attention to is a lot of times when we're working on CTs, we need to be able to find this section here being highlighted as this is where the two CTs combine before they go to the load. And we need to pay special attention to that, that if we're working with a set of CTs, we know where we're disconnecting things to make sure if one of these breakers is in service and one of them is out, that we are not taking the CTs out of an in-service breaker, which can cause a lot of problems. So we need to pay attention to and understand what the CT configuration is and how they're being connected to the load in order to ensure that we would not remove something from service that is important. So some CT circuit safety is CT circuits must always have a load or a burden. They either need to be shorted out to themselves or connected to something. We can't just have a CT with a secondary open and not going to anything. It's very important that to understand that the burden or that load, it restricts the rise of voltage. We can never open a CT circuit. It presents a very dangerous, very high voltage. It's extremely hazardous to personnel to open circuit a CT. You have an extremely high potential if it's opened. You also run the risk of shock or an arc flash. The reason that the CT can't be opened and that voltage rises so much, we're going to use a quick example and run through it in the case of a 2000 to 5 CT. So if 2000 amps flows on the transmission line, that means 5 amps is going to flow through that CT secondary. So a typical resistance you'd see on a secondary CT load would be about 0.2 ohms or 0.2 of an ohm. So if we use some basic Ohm's law, you can see that 5 amps times 0.2 of an ohm is going to give us about a volt on the secondary side. Nothing hazardous there, nothing to worry about. But if we open it and we don't have any sort of resistance on that side that we can see, the CT is going to want to still try and push that 5 amps of current since we have 2000 amps flowing on the primary. So the only thing you can do is try to flow through the capacitance of the CT, which is basically said to say we've created a capacitor, we have current flowing through a conductor, we have air as an insulator, and so that CT is going to try and push the voltage through the air, and it's going to have to, in order to push through the air, it's going to have to raise the voltage. So IEEE standards say that the straight capacitance for a CT is about 200 picofarads. And if we do a little bit of math, we find out that that's well over a million ohms at 60 hertz. And if we do some Ohm's law, we can see that 5 amps times over a million hertz, say 1.3 million hertz or a million ohms, we can get about 65 million volts on the secondary side. There's nothing to say that we actually reach that value, but it can quickly see that in order to get the 5 amps of current that it's wanting to push, it's going to do what it has to. It's going to raise the voltage until it can push current and find a path to ground. CT circuit safety is also about keeping the system integrity intact. You can see the picture here to the right is the result of an open circuit CT. This is considered a minor failure due to that open circuit, but you can see that lug between 3Y2 and 3Y4 where it's burnt up and that CT failed. It caused catastrophic damage to that piece of equipment, had to be replaced. And then when you open circuit a CT, you potentially are simulating circuit faults and you're giving unreliable information to the control center. And we don't want to do either of those things, as it can cause an outage or at the very least cause some confusion. So some procedures for working on CT circuits are always use 2 sets of eyes when working with the CT circuit. Make sure that what you're seeing is really what's there, and have someone else verify that what you're seeing is what's actually there. You always want to work off relevant prints. If you're manipulating a CT circuit or changing it from some older configuration to a newer configuration, make sure you're looking at both sets of prints, old and new. Don't assume that just because you have new prints that everything is going to stay the way it was. Make sure that when you're lifting a wire to make that change, you are seeing the full picture. Double check everything before interacting with that circuit. You don't want to make a mistake and then realize after the fact that something wasn't what you thought. Another important thing is when you check to see if your wire is dead before you lift it, you need to know the minimum range of your test equipment. We've had several instances where we've tripped something off because we thought the circuit was dead, to find out that it had a very small value of current that was relevant. The X-Tech 380950 amp meter that we give everyone has a 1 milliamp minimum resolution and a zero function, so we need to zero it before we use it and then make sure that it's actually dead. We always disconnect at the source whenever possible. So we never cut a CT wire in the middle. We're going to lift it off a terminal block. And lastly, we terminate CT circuits without approval from testing personnel on site. Feel free to, if you guys have any questions, to give us a shout. Have a great day.